for having me over. It's always a pleasure to be here. So I will be talking about strategies for Bootstrap, and it is largely based on this paper that I wrote with Parijat De, who's a postdoc with me in IISc, and Kaushik Ghosh, who's a graduate student of mine in IISc. And there are several related papers which are of relevant, which were written by Fernando Alday over the last couple of years or so. So because this entire program can get very technical, I thought we can build up the story as we go along. So please stop me and ask me questions if something is not clear. So I was thinking that I will give you a broad overview about where this program is going, or where one can contribute to take it forward, rather than actually showing you extremely detailed calculations. I believe Parijat is supposed to be visiting at some point later on, I think this month or maybe early next month, and she can fill you in on the technical details, I suppose. So what is the target for, what is it that we are trying to do here? So the target in this program, Bootstrap program, is to find efficient ways to replace Feynman diagrams for a certain kind of calculations. Efficient ways to replace Feynman diagrams. So in particular, for example, you could consider the epsilon expansion, or you could consider the 1 over n expansion, where you have Feynman diagram results. For certain kinds of calculations, you don't have an elaborate set of results which covers everything, but then you certainly have some results from the Feynman diagram approach. And this is an efficient way in several, as will become clear, that it is quite efficient for a certain kind of calculations. In particular, you do not encounter any infinities. There are no infinities in this approach, and you have an algebraic, if you are clever enough, then you can actually have an algebraic framework to extract critical exponents and the OPE coefficients. So there are a whole bunch of questions where Feynman diagrams are actually inefficient. So one of them is for calculating OPE coefficients. So does everybody know what an OPE coefficient is, or should I revise? Just tell. Yeah, okay, I'll tell you. Okay, so the OPE stands for operator product expansion, something that Wilson introduced to us. So it tells you that if you have one operator phi of x and another operator, does not have to be phi, but for illustrative purposes I'm going to consider identical scalars, and another at phi at 0, and then you can actually expand it in terms of some other local operators. So it will look like some numbers, bunch of numbers that you have to calculate, and some operators, some functions, some position powers of the Lorentz invariant, then some guys which will contain Lorentz indices mu1 to mu l, and then some other guys which carry spin, something like that. So it's an expansion of that kind. So the things that enter this game are knowledge about what are the operators that enter into this kind of, if you want, a Taylor expansion for operators if you want. And also these numbers which are called OPE coefficients. Okay? And you can do that for any spin. And if you knew this information, so in particular if you knew these numbers and also what operators enter this OPE, you will be able to recursively solve any correlation function. In a particular way, yes, in the sense that if you are in the Euclidean signature, then the expansion is sort of naturally arranged in increasing dimension of the operator. The power here actually depends on the dimension of that operator. You can just calculate powers by matching dimensions. So this is of some dimension, and these powers have to soak up the dimension of that operator. But if you were in Lorentzian signature, then it naturally reorganizes itself in powers of twists. Okay, but I'll be mostly talking about Euclidean signatures. So, yeah, yeah. What? Oh, twists. Yeah, twists is just the difference between the conformal dimension and the spin, Lorentz spin. Yeah. So you want to extract OP coefficients for Feynman diagrams. These OP coefficient calculations are quite difficult. Or you could, if you want, you want to say calculate multiple loops. So the state of the art, just for your background information, in the epsilon expansion for the Wilson-Fisher theory is till a year or so back it was 5 loops. So the certain results were known up till 5 loops order. So for example, you could calculate the scaling dimension of phi, which is a fundamental scalar in the theory. So lambda phi to the 4. You calculate the beta function up to 5 loops. You put in an epsilon there. You solve, and then you calculate the critical exponent by solving the Kalan-Simonzik equations. This is known up till 5 loops order. Recently, it is known up till 6 loop order. Of course, you would wonder why would somebody torture himself calculating 6 loops. I don't know.
I mean, something that I've never fully understood is why the epsilon expansion works so well. That is, ultimately you set epsilon equals 1 and you agree very well as Wilson showed.
Only first few orders.
But is it because when you go up to 5 or 6 loops you find extra pi's?
No. In fact, it's not. So I'll give you an example. So that's a question that is a very good question. In fact, so suppose I write down the answer for delta phi, then you see that this one is epsilon square by 108. So you would have thought the 2 loop, wow, it's 1 order lower than that. But then the next order is this is 109 over 11,664 epsilon cubed. And this number and that number are actually comparable. So it's not as if there are some mysterious extra powers that suppress it. It's just it is supposed to be an asymptotic expansion. You truncate up till here, you get a marvelous agreement. You keep adding. Obviously, you can't do that. You have to resum. You have to come up with some resummation techniques, and then. So people have done this. The people have written a book which is around 600 pages. It's called Phi 4. It's readily available on the internet. To calculate 5 loops, you need to calculate around 135 diagrams. And there's a nice anecdote there that some Russians tried to do that in the early 1980s, and they apparently had 18 or so diagrams wrong. I forget the number. And so these Germans actually found the mistakes. And then this was in the early 1990s. It was pre-internet time, so they physically went to Russia to to catch those Russians and hold them down and say that, look, here was a mistake, sort it out. And then they wrote a 664-page book on this. I would encourage you to read today's paper by Parijat and Apratim. Apratim was my graduate student who's now in France, a postdoc with Slava, who actually calculates certain pieces of the 5-loop answer in a paper that is around 20 pages long. Okay, so using bootstrap techniques. So that's sort of illustrative of, if you ask the right question, you can actually extract quite a bit of information from this bootstrap approach. You have to resum. It's supposed to increase the accuracy if you keep more and more loops, if you resum. So you have to do some Padé-Borel resummation. If you, for instance, ask how big is this term compared to this term, I think I can do this calculation in my head. So it's roughly 100. So 2 goes away. So it's like 1 over 100. This is also 1 over 100. It's like same order. So it's like almost 100% error if you set epsilon equal to 1. So that is what Wilson wanted to do. He wanted to do this epsilon expansion, set epsilon equal to 1, and then say that this is the 3D. This is the critical exponent for the 3D Ising model. So that's where the power of this actually lies, an analytic way of making connection with the 3D Ising model, where numerical results, Monte Carlo results are available.
Loop i's appear, the coefficients are all nice.
No, sorry, yes. So this is for delta phi, and then at epsilon to the 4, there are zetas, odd zetas that appear. So zeta 3, some combination zeta 3 will appear at this order. And delta phi square also has the same structure. You start seeing irrational things from epsilon cubed order. So this is the composite operator phi square. So from the Ising model parlance, this is the spin field, and this is the epsilon field or energy operator in the Ising model. So you get irrational objects appearing at this order. What is a curious feature is that at least for these scalar operators, you only encounter odd zeta functions. But for higher spin operators, you start seeing even zeta. So even zetas will be pi squares. Yeah. So this is the kind of things that are available from Feynman diagrams. But of course, you also want to calculate these numbers. And these numbers are not available from Feynman diagrams, except there are indirect arguments for the stress tensor exchange. Apart from that, no results are available from the Feynman diagram approach so far as these numbers are concerned. Okay, so that's a motivation. You want to understand the systematics of the Feynman diagram expansion. The bootstrap is clearly a different, it repackages the information in a different way. If you ask the right question, in some sense it repackages the information that Feynman diagrams give you in a more efficient way. Okay, so just as an aside, these were relevant for the 3D Ising model. What is, yeah, and I'll summarize what is possible from the bootstrap approach in a bit. But just to continue with the motivation, you also want to ask other questions that are more directly relevant to the ADS-CFT correspondence. So for example, suppose you wanted to calculate a loop diagram in ADS space, then there are certain diagrams that you can calculate. For example, if you considered phi to the 4th theory in ADS, so you consider phi to the 4 and you fix the background and you put it in ADS space, you calculate this diagram, you can do the integrals and extract the pole structure that this diagram has. But at the same, but if you try to do a different diagram, say the box diagram, then the results are not available. The calculation is harder. This is not available. And actually, people have in recent times used bootstrap to get information about loop diagrams in ADS where standard techniques based on the usual Wheaton diagram prescriptions are not do not take you to the logical conclusion. That means the resulting integrals are too hard to do. Yes, certain Mellin techniques are available to be when you can write down this this diagram, and then there will be some integrals that you are left to do, but then those integrals are typically very hard. So instead of doing that, you can actually use bootstrap techniques to get the Mellin amplitude for this. Yes, in a way, that was the purpose of this paper, the bunch of papers that we wrote with Rajesh, and yeah. So okay, so this is the preamble. So these are the kind of questions that you would want to ask, where you know, diagrams can take you only so far. So what has been possible so far as the bootstrap technique is concerned? So bootstrap, of course, is an old technique. It was introduced in the 1970s, and it's more than 40 years. So where do things stand? Let me just quickly summarize that. So there are, because I have been involved in one of them, there are two approaches for extracting analytic results from the bootstrap. One of them is what I will call as the usual approach, and I will tell you what usual approach actually means. This was very successfully used in recent times by RRTV. So this is Ratadzi, Richkov, Tony, and Vicky. I will put a subscript FGG because this bootstrap technique was first proposed in the 1970s by Ferrara, Gatto, and Grillo. There is an alternative way, which in the modern parlance is what can be called a new approach or an approach based on Wheaton diagrams, which is basically something that we made precise last year. So this is Gopakumar, Kaviraj, Sen, and myself. And this is based on, again, an old idea by Polyakov, which he introduced in 1974, many, many years before the advent of ADS-CFT. In some sense, quite remarkably, if you work through that paper, you will see that he had the Mellin amplitude for the scalar exchange Wheaton diagrams in a very precise way. So this is what has been successfully used for numerics. So you know the story that people get the most precise numbers for the critical exponents for the 3D Ising model using numerics in the following sense, that compared to Monte Carlo, the order of magnitude for errors that feature in this technique are an order of magnitude lower, a couple of orders of magnitude lower than Monte Carlo techniques. So numerics have been very successful. Analytically, what can be done? So analytically, what you have to have some approximation, and I'll make it clear why this is needed. So for large spin exchange operators, so I wrote down the OPE. So phi times phi in a free theory will have in its OPE the identity operator. So if you consider the 3-point function of the identity operator with phi and phi, you get non-zero. It will also have phi square. Again, in the free theory, you can do it in your head. The 3-point functions of phi, and phi square is also non-zero. But it will also have these kind of operators, which are double field higher spin operators. So this also is non-zero. So this is what I will call OL. And sometimes just to in the modern literature, these are also referred to as the double trace operators, but higher spins. So the anomalous dimensions of these kind of large spin operators, so for L much, much bigger than 1, these can be extracted using the usual bootstrap conditions. I will review how that works in a bit. You can also do something better than this. You can get large spin, large twist. By how do you have a large spin, large twist? You stick in a del square n. So del square n phi in a free theory. So using the equations of motion, del square phi is 0 in the free theory. So these operators do not exist in the free theory, but in the interacting theory they do. So that would be a twist 2n operator. Okay. Well, twist. Well, whatever. Twist is delta minus L. The dimension of this is 2 delta phi plus 2n plus L minus L. So it's 2 delta phi plus 2n. That's the twist. Okay. So in order to extract these informations, actually you only require 1 over L to be the small parameter. You don't really require an explicit small coupling to be there in the theory. Okay, so 1 over L can serve as the expansion parameter. So although I have written this by keeping this free theory or weakly coupled theory picture in mind, but to extract this information, you don't really require that. So Alderman had two things. One of them was for the cusp anomalous dimension, where the delta minus L was log S. So these would actually be suppressed by a further power of spin. So these would be like the double trace operators. Yeah. Yeah. So far as the standard Feynman diagram results are concerned, you can get some leading order. So this is epsilon leading after a lot of work, leading order results. And I will, once I explain the technicalities that go into it, you will understand why it's quite hard to make connection with standard quantum field theory results using this approach, and what you actually need. And as a parenthetical but very relevant comment, this approach does not have any ambiguities, no ambiguities in the basis. And this will become clear as the talk goes along, what I mean by that. So far as this particular thing is concerned, you very easily get the leading order results. This was already shown by Polyakov in a very hard to read and paper full of typos in 1974. Anyhow, I mean, if you go through that, continue, and then you will get the right results. So the leading order is very easy. You don't require any Lagrangian. You just require to make some very mild assumption about what the exchange operators are. So making contact with the Feynman diagram calculations is very easy. If you reformulate this approach that Polyakov had introduced in Mellin space, then actually you can do much better. You can get 3 loop results for both Feynman diagrams and OPE. Sorry, for both anomalous dimensions and OPE, for both anomalous dimensions and OPE quite easily, without calculating any diagrams, of course. And by writing of course you need the help of Mathematica, but then if I can do it, anybody can. Yeah. So, however, in Mellin space there are ambiguities in this basis which are related to contact terms. By what I mean by that is that when you draw a tree-level exchange diagram, you can so a tree-level diagram to 2-2 scattering in ADS space can have an exchange interaction, or it could have also a contact interaction. These contact interactions do not introduce any poles in the Mellin amplitude. They will in Mellin space, these are polynomials. Okay, and so these are these introduce certain ambiguities, which of course affect the basis at a particular order. If you want to have a picture in mind, this approach is just the equality of the S channel OPE. So here you have 2 operators at positions 1 and 2 and 3 and 4. You take these 2 operators close together, these 2 operators close together, and you sum over all possible exchanges. So this is typically what is called the S channel, because of the similarity that it looks like in the, so you have to sum over all these operators. But of course, if you're in Euclidean signature and if you're considering bosonic operators, it does not matter whether you're taking these 2 close together or these 2 close together. So the other way of doing things gives you what is called the T channel. Again, you have to sum over all the exchange operators. So each of these each of these exchanges is what is called a conformal block. The conformal block is by construction consistent with the operator product expansion, but it is not, unless and until you solve this condition, it's not consistent with this is called crossing symmetry. Okay, so this the conformal block expansion of a 4-point function is not automatically consistent with crossing symmetry. So you have to solve this condition to make sure that it is consistent with crossing symmetry. Okay. So here the blocks are consistent with the operator product expansion, but not with crossing symmetry. Crossing symmetry is imposed as a constraint. In this Wheaton diagram approach, the blocks that we use are tree-level exchange Wheaton diagrams. So these are sum of S, T, and U channels. This is automatically crossing symmetric. if you want, and I can't make this more precise because I don't know how to make it more precise, you can think of this as the basis that you would have if you had a quantum effective action for the theory. Yeah, so if you wanted to expand a correlation function, you would use the tree level diagrams of that quantum effective action to expand your answer. Okay. So this is automatically crossing symmetric, but it is not automatically compatible with OPE. So you have to check that the final result is consistent with OPE. In fact, you start getting spurious pores in this approach that you have to remove by solving the consistency condition. So as you can see, the logic has been flipped in the two approaches. Here you're expanding in terms of something that is consistent with OPE, but crossing symmetry is imposed later. Here you're expanding in terms of things that are crossing symmetric, and you're imposing consistency with OPE later. So this is the philosophy. I thought I would continue telling you a few mathematical tidbits which you can remember, because rather than actually going through nitty-gritty details, which I'm happy to explain later on, maybe I can outline the broad picture, and then you can ask me, I can fill in more details as we go along. Any type of vertex means? You mean you can have no, so these are just tree level exchange Wheaton diagrams. So it's only this. There is yeah, so that is the ambiguous piece. So what role the ambiguous piece plays, I will explain. Anyway. Only exchange Wheaton diagrams. That would have been the nicest thing. Unfortunately, the answer is no, because what the logic is that you can compare at the level of the equations what you get from this approach and what you get from that approach. And turns out at the level of the equations, they start differing at a particular order. So the solutions, if you continued solving these equations and this equation, the solutions will start differing. And so unfortunately, this on its own cannot be a consistent basis. Yeah.
So just repeat what you said.
Yeah. So you can set up the equations to solve for the anomalous dimensions of these large spin operators from here, where we know that there are no ambiguities. And you could set up the equations that you would solve for the anomalous dimensions of these same large spin operators using this. They are in agreement to all orders in inverse spin, only up to a certain order in the, see there's some small parameter that you're expanding, so you're putting in a gamma here. Okay, so this gamma is a function of L. So up to order gamma, but to all orders in inverse spin. Does that make sense? So this is like, you're saying that suppose there is a 1 over n, let's be very precise, so suppose there's a 1 over n, then the answer actually can be written as an in this form, gamma 1 L to the power hash plus 2 and so on. So all these terms are going to agree between the two approaches, but they are going to start differing at order 1 over n squared. Okay, and the difference can be attributed to the fact that there are these polynomial ambiguities here, which we haven't fixed. So there's nothing to be alarmed. These differences are expected, and you need to have some other physical principle or some other clever way of fixing these ambiguities.
But is it that those ambiguities are fixed by the requirement of the good operator expansion, or even after imposing that, you are left with?
No, so the ambiguities are there in the basis, so you require some other fundamental principle. So one of them is, one of the ways of fixing this ambiguity is to demand that you have consistent factorization. What that means by that is that you're allowed to, the bulk-to-bulk propagator, you can split it up into tree diagrams. So a bulk-to-bulk propagator, so this was a bulk-to-bulk propagator, and this is called the split function representation. This the bulk-to-bulk propagator has a representation where you're taking this bulk point all the way to the boundary, and then you're integrating over all these exchanges. So this has become now the product of two trees. So if you want, this is the equivalent of the Feynman tree theorem in ADS space. So these additional consistency conditions have to be satisfied.
You should go on. What is this final tree? I don't know this.
Oh, this is you can split any loop diagram into product of trees.
You cut them?
Yeah, cut them and then you glue them.
But you cut them, say, on shell, or what do you do?
So the usual, so the thing that probably we are familiar with in quantum field theory is that you have a loop and you cut it and you place that on shell, and that gives you the imaginary part of the loop diagram, right? That is what we are familiar with, yeah. So
This is analogous
yeah, that is analogous to.
for tree diagrams itself, huh? Where you take points to the boundary, you get some additional.
Yes.
There was no loop to begin with.
No, here there was no loop. Yeah. But the tree diagram basis itself is you could add this diagram. The question is whether you can add anything, or in order for this to be basis, does this have to be fixed? Whatever you're saying. Yeah.
So it's the question of whether to include that or not.
Yes. I mean, the thing is that, of course, if you had just 5 to the 4, suppose you had an ADS dual and you added 5 to the 4, this would be a vertex in that theory. But then you could also have del phi raised to some power, so those would have some higher derivatives.
So that would mean that you would have to include this diagram.
Yeah, you would have to. You will have to include such a diagram to make this into a good basis. That is the bottom line of this. Yes, it's a good question. I don't know the answer to that. The only answer that I can give you is that it has to satisfy all the consistency conditions for scattering amplitudes in ADS, and then we would expect it to be a good basis.
You should go there. First of all, I mean, are you saying that in general the bootstrap, if you take the left-hand side, it need not have a unique solution, right? It could give, just the bootstrap consistency could give you more than one
Yeah.
solution. Are you saying correspondingly on the right-hand side also that even after you impose consistency of OP and crossing symmetry, there can be more than one solution and you can't match them? Or are you saying that the approach on the right-hand side, where you begin with crossing symmetry and you impose the OP as a requirement, is not enough to get a consistent solution? You have these additional.
Yeah, there are these additional ambiguities that you have to fix using some physical principle. That is what I'm saying. Okay, they will give you easy. I mean, this is a very nice basis because it gives you the standard results that you would obtain from Feynman diagrams very easily, up to 3 loop order, which this approach cannot do. And it will become once I explain the technicalities, it will become clear why it cannot do.
And you're saying ambiguities basically correspond to different
Contact terms that you can, yes.
But you can't have any coefficient for the contact.
No, you can't. Yeah.
So there's some restrictions that OP and crossing
Yes.
symmetry will give, but it leaves the possibility.
Yes. Yes.
Why can't you have loop diagrams that would?
You can. But then as I said that you could try to modify the basis by including loop diagrams. That may be another way of expanding the basis. This is, as I said, so suppose you did have a quantum effective action. Then what would you do in that theory? You would not calculate loops in that theory.
I don't quite see why this would be analogous to the quantum effective action. So is that the larger issue that you choose not to include the loop diagram?
No, I'll give you a better answer. Just hang on a bit. So I will give you a better answer. I will be able to actually give you a derivation of, by starting from the expansion in terms of the conformal blocks, how you get the tree level exchange Wheaton diagram. So just hang on for a little bit. Yeah. Okay. So just so that we are not all lost in already, let me just give you some mathematical tidbits, just for you to remember. I'm doing atrociously with time, so I think, okay. So one thing that you should remember, just for the background knowledge, is that the what we want to make use of is what is called Mellin space. So this is some analog of the SNT variables that you have in the in flat space Mandelstam invariants if you want. So we want to take the Mellin transform of the 4-point function. So let me write down a 4-point function, maybe just to make sure that you're not all lost. So if you have a 4-point function of 4 identical scalars, you can do it for anything that you want with a lot of work. But suppose it's identical scalars, then your answer is going to look like this. So there is a position dependence of this kind that you pull out, and then conformal invariance tells you that the rest of the functional dependence is going to be through these conformal cross ratios. Okay, and you can take a Mellin transform of this. So this is what I mean by taking a Mellin transform. That you write this as u to the power s, v to the power t, and it's an integral from minus I infinity to I infinity with some possible shifts. I can explain what these shifts mean if you want later on. But then this is what I'll call the Mellin amplitude after I have factored out a certain conventional piece which looks like this. Okay, this measure is factored out because this measure has information about the double trace operators in the large N language. Okay, so here the poles of S, the fact that there are poles at S equal to delta phi plus n tells you that there are double trace operators in the large N theory, precisely those values. So this is what I mean by the Mellin amplitude. Okay, you can calculate using the standard ADS CFT rules the Mellin amplitude for scalar exchange. The thing that you have to remember here is that in Mellin space, this actually is a 3f2 hypergeometric function. Okay? M, yes, this is the M. So that's one thing that you have to remember, that this 3f2 is going to play a role everywhere.
And so it depends in general on the mass of this scalar,
Yes.
but it's always this 3f2 is the set of vectors.
Yes. Okay. The other mathematical tidbit that I wanted to tell you, and this was going to be relevant if I manage to finish my talk, is there is something called the reciprocity principle. Which tells you that so if you are considering these double trace operators with spin, so these kind of operators, so of course they are labeled by the spin L. The anomalous dimensions of these operators will also be a function of L. So gamma, which is anomalous dimension, will be a function of L. And you would have thought that naively, if at large spin, this must this probably will go like 1 over L to some power and then subleading powers of 1 over L. That's what it looks like. But actually, if there are results that Korczynski and others found, which tells you that L is not a very efficient variable to expand in, but rather the more efficient variable is what is called the conformal spin. So this is called conformal spin. So J square is related to this L through the following relation: delta phi plus L plus gamma L by 2. Gamma L is the anomalous dimension of the spin L operator. So this is what you would like to expand in. Okay. And the last mathematical tidbit that I wanted to give you, which is going to be relevant in my story, is what is called a continuous Hahn polynomial. Yeah.
So I
L plus half. Right?
Yeah.
It seems like it. So is the relation in large thing or also like large and also something involved in that relation? How?
So the results that they had derived was in the large N.
Large.
Okay.
So it's like if I come to say anonymous dimensions up to 2,
Yeah.
and then you sort of rewrite it.
Yeah. So they had some results by doing explicit calculations, but there was a proof of this from the bootstrap by Alde and Bissey around 2 years back, where they proved that this is true for all loops. It's not just true for the leading 1 over n or whatever. Yeah. It turns out that in Mellin space, there is a natural basis that is given to us for whatever reasons. These are called continuous Hahn polynomials. These are also related to 3f2s, except that they are polynomials. So one of the entries of the 3f2 is minus L. So those of you who are familiar with hypergeometric functions, if there is a negative integer in the top entry, then the expansion terminates. And very specifically, these are the kind of polynomials that enter our expansions. There are limits of these polynomials that you can take. For example, you can take sigma by t fixed, but sigma and t both large, and that in that limit, these polynomials become the familiar Legendre polynomials.
So what is sigma in the problem?
Oh, so S. This is S if you want. Yeah. Yeah. Now, of course, we want to do, as I said, there's a large spin story that I wanted to say. So then, of course, the natural thing to expect is that you need the large L limit of these or large L approximations of these. And quite unfortunately, the asymptotic expansion for these polynomials weren't known in the mathematical literature, at least in any useful way, useful form. So we have to derive this. So we now have a large spin in our paper. We derived it. So let me.
So that would be the radius length scale entering this polynomial.
This L is a spin.
Yeah.
Yeah. And the ADS length scale is going to be in the large. So you, in order to extract the Legendre polynomials, you have to take this limit, and you also take the limit where. So S is evaluated typically. There is a gamma function that enters. S is evaluated at the conformal dimension. This also you take large. So this is it's through this that the ADS length scale is going to enter.
So it would be equivalent to taking
Yeah.
getting the polynomial in flat space.
Yes. Yes. So I suppose in general in arbitrary dimensions these are the Gegenbauer polynomials. Okay. So there's an expansion, and I'm telling this to you because I found this from a mathematical perspective quite intriguing. The expansion here actually involves precisely this J, the conformal spin that I wrote there. Except for J, you're going to see S, but S has a pole at the has a pole somewhere. So actually, what you do is you replace this object delta phi plus gamma L by 2 by S, and these continuous Hahn polynomials have an expansion precisely in terms of these conformals, the conformal spin. So it has got a well-defined expansion. I will just write it very schematically, and why this is of interest will become clear, I suppose. And the coefficients here are known. The coefficients here involve what are called generalized Bernoulli polynomials. So there's a generalization to the Bernoulli polynomials. Bernoulli polynomials have a generating function. So there's a generalization for that, gives you the generalized Bernoulli polynomials. But these generalized Bernoulli polynomials also, as a mathematical aside, I don't know whether there is anything profound to this or not, satisfy kind of a duality, channel duality relation. So the most familiar channel duality relation that string theorists have encountered appears from the Veneziano amplitude. So you have a beta function, and this beta function has this very nice property that you can expand either in terms of this pole or this poles without adding any regular piece. So that is an exact statement. That pole expansion is an exact statement. And this beta function is one of the mathematical functions that have this. Gamma functions don't. For example, suppose you have gamma of s, and then you said that you want to expand it in terms of the poles of this. Then you would have to add a regular piece, which is the what is it? Regularized gamma function. What is it called? Incomplete gamma function. It's an incomplete gamma function. Okay.
And certainly more than the sum of its form.
Yes, exactly. Yeah, but the beta function isn't. So these generalized Bernoulli polynomials satisfy some kind of a higher order duality relation. So which actually look like this. I'll write it down. This is something that doesn't appear to have been used in the physics literature ever. And I don't even know whether there's a use for these to be found. This is equal to now, so you see that there are higher order poles in the variables s and t. If it was a beta function, j would be equal to 1, there would be simple poles, k would be equal to 1. When j and k are equal to 1, this is precisely the expansion of a beta function. So this is precisely the string theory Venetian amplitude relation. So these are in some sense generalizations of those. I don't know if there's any. I thought this was interesting enough to make a note of, so I thought I should let you know that there is something along these lines. Okay, so in the last 5 or 10 minutes, or 10 minutes perhaps, let me just tell you about how to use the bootstrap conditions to extract anything. Okay.
What did you do? You wrote 3f2 and expanded it in powers of k.
Yes, in conformal spin, it turns out this is not a trivial thing. You have to use some tricks that were invented by Wilson. So this Wilson is not Ken Wilson, but there's a mathematician Wilson as well. So you have to use some tricks that this Wilson invented. So instead of a 3f2, you have to lift it to a 4. Actually, you lift it to a 7f6, and then through something or the other, you get right through the 3f2. It's there in the appendix of our paper, how to derive the asymptotics. Okay. So these people who do hypergeometric functions, I mean, so one thing is that if you read any mathematical literature on hypergeometric functions, you will feel that you are understanding it. Except that ultimately the identities that they derive appear to be quite magical in the end. And there's all these kind of resummation identities that you can have, very well-known identities, some of which you have heard of, which are called Chu-Vandermonde identity, or the Gauss resummation formula, or the Salschuetzian, that appear quite nice.
What is the general, you have to tell
I will.
us the general idea is what you have an integral representation,
Yes.
and you look at some, is that
I will now tie all this together. Okay? Yes. So the general policy in the usual approach where I said that you expand in terms of, you have this relation between the two channels s equal to t. So let me just explicitly write down the relation. So what you have is summation over operator product expansion, more precisely these are OP coefficient squared, times in the variables u delta minus L by 2 plus m. M is an integer, it labels the descendant. So here as usual this is the exchange operator, dimension of the exchange operator, this is the spin, this labels the descendant, and there is some function of v, and yeah, so there is some function of v. So this is how you can write the S channel. Okay, so this and you can there is an expression, there is a known expression that you can write in Mellin space for this which looks like the following. So the S channel looks like u to the power s, v to the power t, and now this gamma of twist by 2 minus s, gamma of shadow twist by 2 minus s divided by gamma of delta phi minus s square times some polynomial here, in the variables s and t, which also depend on delta and L. These are called Mach polynomials, and times this measure factor that I pulled out earlier. Okay. So this is the S channel, and you have to sum over all the exchanges. So tau is the twist, so there is the C delta L that you have to sum over. So it looks like that. Okay. Okay. Let me write on the T channel, and then we'll analyze the pole structure of these two. So the T channel is obtained from the S channel expression by doing the following replacement. You replace S goes to T plus delta phi, and T goes to S minus delta phi. And what you land up is U by V to the power delta phi times an integral tau by 2 minus T minus delta phi times the same shadow piece. So let's call this shadow. I won't write it out explicitly. Gamma function divided by gamma of minus T square times some polynomial with these replaced. So T plus delta phi S minus delta phi. And now this has a feature that this is invariant under that replacement. So this just goes for the right. Okay, so that's the left hand side of this crossing symmetry equation, crossing symmetry condition, and this is the right hand side of the crossing symmetry condition. Okay. Now notice what is happening to the poles. Now, so far as T poles are concerned, so you can close the contour on the right. So you'll pick up the poles that come from here. Okay, this is a polynomial that does not contribute to any T poles. You pick up poles from here. So these are all double poles. So double poles would mean that you will get log V's here. Specifically, you will get things that look like V to some integer times log V. Okay. But look at poles here. There is a gamma of minus T square. So that does not contribute. You have simple poles here. Okay. And there is some power dependence here. So on the right hand side, we do not have any log V's. So the right hand side, the leading singularity is going to be V to the power minus delta phi. Okay, delta phi is typically bigger than 1. Suppose your in 4 dimensions are higher. So delta phi is bigger than 0. So this goes like 1 over V to some power. Is that clear? So this goes like 1 over V to some power, but then this goes maximum like log V. And in fact, in the V going to 0 limit, except for log V, these are not singular. But here you have a singularity. Okay. So that tells you, that is the first indication that you have to sum over, in order to reproduce this power law singularity, you have to sum over an infinite number of operators. By summing over a finite number of operators, there is no way that you can convert log V singularity into a power law singularity. Okay. Okay. Now let us look at the S poles. So here in the S channel, the only poles that come from are from here. Okay, this and this cancel off. I'm closing the contour on the right because I want to be in the limit that U goes to 0 and V is also less than 1. So I want to pick up more and more subleading terms in S. So I will close the contour on the right. Okay, so that gives rise to U to the power tau by 2. This is precisely this, tau by 2 plus M plus M. Okay. Now consider what's happening in the T channel.
I suggest from the gamma tau.
This one, yeah. Now consider what's happening in the T channel. So T channel, there are double poles here. This is a polynomial in S. There is no T dependence. There is no S dependence here. There is an S dependence here. So the U power is governed by this gamma function. So the U dependence in the T channel will look like U to the power delta phi plus N log U. Okay. From here. So this also comes down.
There also.
Yeah, this factor is also there. So this is gamma of delta phi minus S square. So that's going to give rise to a power like this. Okay. So on the left hand side, you have U to the power tau by 2. And on the right hand side, you have u to the power delta phi plus n log u. Okay. So one way of getting a log u from this is to say that you have some tau by 2 is delta phi plus n plus some small gamma. Okay. If tau by 2 was delta phi plus n plus some small gamma and you expanded that, then you're going to get gamma u to the power delta phi plus n log u. Okay. So this already gives you a condition that there should be an infinite number of operators whose deltas, so tau is delta minus L, so delta minus L by 2 is delta phi plus n. This is some small parameter, I'll put gamma by 2 here, plus n plus gamma by 2. So delta should be equal to plus gamma plus L. So there should be an infinite number of such operators for the powers to match.
What was tau in this in both the left and right hand side?
So tau is always delta minus L.
So delta. Infinite number of terms because of this n.
Yes, because of yes. So that actually adjusts. So I'm calling that a single integer. Okay. Yeah. And tilde if you want. Okay. So that's an easy way of realizing that there should be these kind of operators for the powers to match up. And then of course the next question that you ask is, suppose there were these operators, then can you, so remember that the previous lesson that we learned is that there is a v to the power minus delta phi, and we want to reproduce that singularity as well. So by putting in these kind of operators, can you reproduce that singularity? Okay. Okay. So this is where the large J form is going to come in handy. So what happens in this story is that if we were looking at u to the power delta phi with n equal to 0, okay, if you were looking at that condition, then this the Mellin transform involves, instead of the Mach polynomial, these continuous Hahn polynomials. Okay. Continuous Hahn, I have worked out the asymptotics. There is an inverse power of 1 over j. There was this e to the power minus 2s minus 2t, and sorry, plus 2t plus some integers. So here is a t dependence. In order for you to get v to the power minus delta phi, you need, from the perspective of the S channel, to convert the double pole that is here. Okay, there's a double pole here that gives rise to that. You want to convert that double pole into a simple pole, because the way that you get a, so if there was a t plus delta phi, if there was a term like this, then this would become on contour integration v to the power minus delta phi. Okay. Now see, everything is falling into place because, okay, I have erased that unfortunately, but then this continuous Hahn polynomial also had a gamma of minus t square in the denominator. This continuous Hahn. No. So this is only the left hand side. Only the left hand side. Okay. So this continuous Hahn polynomial, you're using the asymptotic form. It has got a gamma of minus t square in the denominator. It gets rid of this gamma of minus t square, which means at this stage the double poles are gone. But somehow you have to get a simple pole. So how do you get a simple pole? You have to sum over all j's or all l's. Okay. And how do you do that? So there will be some extra function of j also, which can be fixed by demanding that you produce a right pole in t. But how do you do this sum? Any idea? How do you do such a sum? So suppose I put in, suppose I do the sum from L equals to some lower cutoff to higher cutoff, some infinity. What would you do? Matsubara. Okay. I mean, in the maths parlance, there is a, what is it called? Do you remember? The maths question. It's called the Euler-Maclaurin summation formula. Some j. In fact, it will turn out that this, in order to produce the pole correctly, you will, this has to have the form, there could be some log j's, because of course if I'm expanding in gamma, then I will start generating higher poles. So, so for example, you will not only have, suppose I'm doing that on the left hand side, you will not only have log u, but you're also going to have log u square, which means that there is a double pole. That comes from expanding a simple pole using some small parameter. So all those have to be reproduced.
These operators that you concluded from the analysis of the simulated structure in U,
Yes.
those don't help you to get the log V singularity from the power of singularity in U.
So I'm summing over the operators on the left-hand side, these operators on the left-hand side, so that this log V gets converted into power law. Probably you are asking that suppose I plugged in the same operators on the right-hand side, what is going to happen? That's a very good question. In fact, we are actually assuming that the OPE actually does not have just those operators, but also some operator like the stress tensor in the spectrum, which is distinct from that, so that we can consider the exchange of that particular. Otherwise, we would have to sum over those operators as well, and that is exactly what happens in the epsilon expansion. So for the purpose of this, you can think that there are these operators which come from the composites of phi and phi, but then there's also other operators like the stress tensor or something else, which is distinct from these operators that is there. And we want to reproduce that pole from the left-hand side. Is the logic clear? I'm sorry, I'm having to rush, but I don't want to hold you for longer than necessary. But is the logic clear? What is it that we are trying to do? And let me write down the Euler-Maclaurin summation formula, and then perhaps it will become clear how you get go from here to a pole. So if you have something like this, then this actually looks like 1 over L plus some shift to some power, say A, and then there's some shift minus 1 to some power, this is also A. So you have to do this sum. Okay. The way that you do this sum is you first do an binomial expansion by treating this to be large, because L is large. So the summation is from capital L to infinity. So there's it will turn out that this lower cutoff that you're putting in is not going to play any role in the analysis. And then you will get something after using the binomial, so let's call this alpha. After using the binomial theorem, you're going to get this.
So even if you look at these other operators in this C-channel, wouldn't you end up concluding that you would have to have this crowd of operators associated to that exchange, which would contribute the log?
Repeat.
No, I mean you said that you want to produce the poles from these other operators.
Yeah, you will you will end up concluding that there are also the double field operators made up of multiple T's. Yes.
And I mean essentially
Yes.
the logic from here to there is
Yes. 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 Yes.
So now we are getting more.
Yes. 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 Correct. And those would correspond to different poles, because you are here you are trying to reproduce this pole, and there you would try to reproduce some a different pole. Yeah. That's exactly the game of bootstrap, that you first get some information and then use that information, plug it back into the same equations, and try to get some more information, and that's you're bootstrapping your way through. Anyhow, so there's a Euler-Maclaurin summation formula that you can write down from here. Essentially, you will need to do an integral that looks like this: dl tilde over L tilde plus A raised to some power. The S and T dependence is through this alpha, okay? The T dependence is here. T dependence is here, and you're integrating from L naught to infinity. You should be able to do this in your head. No? Okay, good. Anyway, now you're Mathematica culture, so you go to Mathematica, ask it. So anyway, you are going to get a pole. You are going to get a pole here, and plus regular. So I'm not interested in the regular terms, because the T dependence is through here, so you get a pole, simple pole in T by doing the summation. Okay, and the cutoff actually enters into the regular pieces, so the cutoff goes away. I mean, it does not depend on the cutoff. Okay, And it turns out that you can actually, to reproduce the contribution of, say, the stress tensor in the T channel, you can get the entire asymptotic series. It's not just the leading term in 1 over j, but you can get the entire asymptotic series, which ultimately leads to the production of this operator in the T channel. Okay, and you can give a closed form expression. That's what we worked out in our paper. And that closed form expression has some nice features. So let me just conclude in 2 minutes. So the closed form expression in the nice, what is the nice feature here? So
Sorry, slightly. So you have this equality.
yes,
And you learned that you needed a certain Dauer operator. and
Yes.
so on. And after that, you also learned something about the gammas?
yes, yes. Because you want to go and reproduce this, the appropriate V powers. Okay. So if you did not have gamma behaving like some specific inverse power of 1 over L, using this Euler-Maclaurin summation formula, you will not be able to produce those specific V powers. That is the logic. And so ultimately you end up getting an anomalous dimension for these operators. You can determine that. You can write that down as Ck over j to the power 2k, and you can sum over that. So there is actually there's some 2 delta phi or something, some twist that some other factor that you have to factor out, but ultimately you can write it like that, and you can give a closed form expression for the Ck. Okay. Now, then of course, what do you ask? As a physicist, you would ask, okay, what does Ck plus 1 over Ck behave like? Okay. So it turns out that so here, of course, I described the calculation pretending that there was a stress tensor exchange on the right hand side, but it could be any operator exchange on the right hand side. It turns out that the asymptotics of Ck plus 1 over Ck does not care about what you're exchanging on the right hand side. It's always universal. And so there's some, if you plot, or if you consider this, then this actually goes like m square, m by pi, k by pi. Yeah. Okay. And then, okay, now let's process this information. So this goes like k by pi, which actually tells you that larger and larger k's that you go, these coefficients are becoming bigger and bigger. Okay, so it's clearly is an asymptotic series. So does this asymptotic series have some nice properties? So it turns out that this asymptotic series is what is called a Stieltjes series. Now I don't have time to tell you what the Stieltjes series is, but the Stieltjes series has a property that tells you that this, as a function of j, is analytic everywhere in the complex j plane, except for a branch cut that runs on the negative axis. Okay, so that's the analytic property
The analytic property is gamma
of j of the L, the conformal spin. Okay, so you want to make j, you want to consider j to be you want to consider the analyticity property as a function of j, as a function of angular momentum.
But why does the series is over, you mean after sum the series
Yes.
in some suitable way? This is the
Yes.
analytic property of
Yes.
the resulting
Yes.
function.
Yes, in particular, actually, by exploiting this property, there are some more properties of the Stieltjes series which I can tell you about.
Okay.
Some mathematical properties. You conclude that there is a branch cut running all the way in the negative real axis, and in the J complex J plane.
The J complex
Yeah, in the
plane
complex.
plotting gamma L, is it?
In the J complex plane, I'm asking where are things analytic?
You mean gamma L?
Gamma L.
Okay.
Yeah, yeah,
All right, I understand. I see.
yeah.
So gamma L has a branch cut like
Yes.
this in the J.
Yes.
Right.
And so that means that you using a dispersion relation,
I see.
you can extract these coefficients. So that's the bottom line, that there is a dispersion relation technique to extract these coefficients by exploiting the analyticity property in the complex J plane. This was pointed out, or this was proved in the by Simon Karen-Huot earlier this year, that you can do this, but I mean, this is another way of reaching the same conclusion, that you have analyticity in the complex J plane, and there is some dispersion relation way of extracting these anomalous dimensions themselves. I mean, Karen-Huot actually gave an inversion formula for the OP coefficients, but you have something similar for even anomalous dimensions. So that's the lesson that you learn. There are a bunch of other applications also for this closed form expression, in particular actually by doing almost nothing. I'll leave it as an exercise for anybody who wants to get into the bootstrap game, that the anomalous the dimension of delta phi square is known to be 2 minus 2/3 epsilon. Okay, so this is something. Now here we have derived the conformal or the anomalous dimension of these operators, these double field operators. Okay, so the exercise that you can do is that these anomalous dimensions are known. These anomalous dimensions gamma L these are known to be epsilon square by 54, 1 minus 6 over L into L plus 1. And you don't have to do a bootstrap calculation to determine this. This was already known from the first original work by Wilson. So Wilson did this calculation, and you should read Wilson's paper, because there is a self-contradiction in his review with Kogut and his PRD paper. In his review with Kogut, he says that details will be found here. In his PRD paper, he says details will be found here. So ultimately, no details are given. And but anyway, so what can you do with this? So look, here it starts at epsilon square order. Oh, that is there. Epsilon hasn't entered here, so I'm going to. So you can think of. There are these functions will be a function of dimension, and delta phi is also going to enter. So you put dimension equals to 4 minus epsilon, and delta phi to be 1 minus epsilon by 2, and plus epsilon square by 108. Okay, so you can put that this information into the formula for gamma L. It will turn out that you get this.
But the anomalous dimension was exactly good.
Yeah, it was exact in functions of d and delta phi. Okay, so you could take that expression and expand. Okay. Now the reason why I'm pointing this out is that look, this is epsilon square and this is epsilon. Okay, so here's a puzzle. How do you? So of course I've got an asymptotic series. Okay, but not in terms of L, but in terms of J, and that's important. So if you go use the reciprocity principle, convert these into functions of J, you will recover precisely this result. So if you set L equal to 0 in that answer. So you take this answer, okay, this is L. So we know that there is some principle called the reciprocity principle, which tells you that instead of L, you should actually, this actually started its life by as a function of J. Then, so J square here is delta phi plus gamma L by 2 minus 1 times delta phi plus gamma L by 2. So, oh sorry, there is L as well. I forgot the L, the plus L. Okay. So here is your L. So this one is L in the bare dimension of delta phi is 1. So throw the anomalous dimension away, so you get L from here, and this is L plus 1, because this is 1. So this is L plus 1. This is 0. So that's the origin of this factor L into L plus 1. What I'm saying is that, so the reciprocity principle tells you that instead of this, I should be using this whole thing. Now, of course, when you use the whole thing, you are allowed to set L equal to 0, which you're not allowed to set here. But you are allowed to set L equal to 0 here, because it's now regularized. Okay. So what are you going to get? So you're going to get 1 here, and this minus 1 here. This begins its life at epsilon square order. So this is epsilon square, this guy, and then this is regularized. So this begins its life as 1, right? So because of this one. So so you.
So 1 over epsilon square cancels the epsilon square in front, you're saying, and giving some
Yeah, sorry, I said something wrong. This actually begins its life. So once you expand this, there'll be an epsilon piece that is left over. So we can work this out. This is L plus 1 minus epsilon by 2 minus 1. So this epsilon by 2 is left over. Okay. So actually, this guy, when you set L equal to 0, is order epsilon. So this is 1 minus epsilon by 2. Okay. So when you actually set L equal to 0, you're going to get something order epsilon here. So that converts this epsilon square into this epsilon. Okay. So there's a couple of lines of more algebra, but then it's basically you recover the leading order anomalous dimension by through this reciprocity principle if you want. But anyhow, going beyond this in the epsilon expansion from the bootstrap is extremely hard in this traditional approach. So that's why we had looked into this other framework using Wheaton diagrams, and that allows you to get a bit more mileage. And you had asked, let me just answer your question. You had asked, how do I go from, well, let me paraphrase your question. You had asked, how do I go from the usual conformal block expansion to the Wheaton diagram expansion? And that, the way that you do that is this. So this is your MST. Okay. You now make use of the fact that you rewrite this as a product of two beta functions. Okay. You can rewrite this as a product of two beta functions. One of the beta functions will have tau by 2 minus s as its argument. The other one is going to have tau bar by 2 minus s as its argument. And why I want to do that is beta functions have this nice expansion in terms of poles. Okay. So you expand in terms of only these poles. The rest you do a Taylor expansion, the rest of the piece. So beta times beta, the first beta you're expanding in terms of this pole, the second beta you're expanding, Taylor expanding around this pole. Is that clear? The result is going to be identical to the Wheaton diagram calculation that you would do in using ADS-CFT techniques. And then that gives you a systematic way of recognizing what the polynomial pieces are, because that's the leading order term in the Taylor expansion in the second argument. So the things that you're throwing away are polynomials. Okay, so we are thinking about how to fix that, but we don't have anything concrete as yet. So the bottom line is that I think we are just about beginning to develop a systematic set of tools to understand how to extract information using bootstrap. I think there's a lot left to be done, but also I think it's fun because there are these relations that Feynman diagrams actually does not tell you exist, but which are actually there, which arise from the bootstrap calculation. For example, this relation that there are pieces of the 5 loop anomalous dimensions. This is only up till epsilon square, but you can go all the way up till 5 loops. These pieces can be fixed entirely in terms of the lower available data. You don't really have to do a Feynman diagram calculation. So using standard available results, you can actually fix some of these pieces by exploiting the bootstrap. Yeah, so I think I just outlined what are some of the standard techniques that people are using now, or what they are, but I do not have time to tell you anything about putting in external operators. That is also something that people are working extensively on. External operators carrying spin. So if you have external operators carrying spin, the technology, there's a whole technology that builds on some work by Dirac in the 1930s, and now it's become a very tedious, but at least the framework is there. People have extracted results from that. They have extracted the Hoffman-Maldacena bounds.
You mean source change the Lagrange, or what is
No, the external operator carrying spin. So it's just instead of phi, so you consider say in the Venn theory you're considering J mu, J nu, phi, an operator of this, a correlation function of this kind. And what condition, what do you extract from the bootstrap by considering this?
J's are not operators in this theory.
No, they are operators in the theory. So in the they could be the U1 current.
So you mean 4-point functions of
4-point functions of
involving two operators
of
like
scalars and higher spins, and this does not have to be restricted to this. You can consider stress tensor, you can consider any spin that you want, and so that technology is becoming available. People are exploiting it, and
we now have the word identities for current observation and conditioning.
For example, yeah, exactly. For example, but it does not have to be conserved current. It could be some higher spin operator in your theory, for example, with some anomalous dimension, and then that. I mean, say if you wanted to do it in the Chern-Simons theory, you put in some really high spin operator as an external operator, and then you see how things get constrained.
Those are also conserved approximately.
Approximately, but then yeah, not completely, but yeah. So you don't have the. I mean, the word identity is approximate, yeah.
I see.
And yeah, so people have been able to extract these so-called Hoffman-Malda-Senna bounds or the CEMZ bounds. You must have heard of this through talks here. So CEMZ is Kaman, Wedelstein, Malda-Senna, and Zuboydov. So people have had nice things to say about those things, just building on the bootstrap idea. So basically, I feel that there's a lot left to be done. Mathematically, I think the most technically challenging problem is to come up with compact expressions for these Mach polynomials. So in this approximation where I set n equal to 0, this becomes continuous Hans, but we don't have that kind of a thing when n is not equal to 0. I think technically that would be interesting. Or you identify certain limits where you take s and t to be very large and then try to simplify these. Say you consider the Regel limit, or you make use of some analytic continuation properties and try to extract information. So I think you just have to ask the right question, you have to be clever enough, and I think these kind of conditions will give you a lot of insight, not only into holography, but I think into just independent of holography into quantum field theory. So yeah. So let me stop there. Thanks for listening.
Graphing is good. It's like, for example, if u goes to 0, v goes to 0, but p is ratio of this. You have a huge integration of this. It doesn't buy you anything in this. The reason I'm asking is that, like, in the conventional graphing expression, right? I don't.
That is the double Lightphone limit.
Yeah, the double Lightphone limit. The FUV, how it behaves. Suppose take this node for some field. In this, will it buy you something so that you can compare and then fix your amplitude usage?
If you are interested only in the leading terms, say in the then I think
but otherwise, this double Lightphone limit is not going to buy you much in this game.
No, what will buy you something is the Regel limit. The Regel limit is you go onto the film sheet by doing analytic techniques. That actually does buy you. Without working, well, it appears without working too hard. But we can talk about that actually.
One question if I may ask, which is how far has the technology advanced? That is, presumably the idea here is not to keep expanding or improving on the epsilon expansion. Right. So perhaps the idea is, can we, for conformal field theories, we just haven't been able to solve it all, but we may have some idea exist, obtain anomalous dimension.
For example, this did not rely on the epsilon expansion. There was no, when I set up these equations, they did not have any perturbative fucking expansion.
Right. So maybe I missed that. So did you get exact? I mean,
Yeah.
no perturbative.
Yes. So this answer is non-perturbative in the sense that the expansion parameter is 1 over n. So there is an epsilon, there is no 1 over n. So at least for this sector of the theory, these are supposed to be.
So what is so the thinking is take any the data of the conformal field theory of interest, where would that be here? That is central charge about is it just
So ultimately when you actually solve so when you solve this, you would actually get an answer in terms of delta pi dimension and the spin. The answer would be in that.
I see. So if you had a scalar with dimension delta pi and you make this of delta pi with many derivatives and pi again, then that would have a just depending on delta pi.
Yes. So for example, using the same formula, you can get the 1 over n result. So I just give an example for the epsilon expansion. But you get the
Now, the CFT only goes into delta phi
For these kind of operators.
for these kind of operators, and these were these operators phi with a
Yeah.
string of derivative.
Yeah. So, but just following up on your question, of course, one of the things that would be nice to have is right now we are just making connection with standard expansion parameters or some things that are sort of some logically consistent with quantum field theory, say epsilon, 1 over n, so on. But it would be nice to identify some other expansion parameter. It does not have to be epsilon or 1 over n. It could be in terms of, say, the difference between delta phi and the z image. Treat that as an expansion parameter and see whether you can get a nicer result of maybe something that converges faster, something along those lines. And of course, the grander thing is what he probably had in mind. I don't know how feasible it is, but he sort of wanted to solve it along for the principal field, and then analytically continue and get real physically interesting theories. Yeah, so whether that could be made into